Hi, this is Dr. John Bergdorf. In an earlier video, we introduced the concepts of relations and functions and the accompanying ideas of domain and range. If you haven't had a chance to look at that video yet, I'd urge you to look at that one first. We're going to build on those concepts to talk specifically in this lesson about relations and functions that are defined by equations. What we're going to see in the rest of college algebra and beyond is that the most common type of relation and function that we'll see is a function or relation that's defined by some sort of an equation. But before we look at that, let's just quickly review the concepts we've seen already. A relation is a set of ordered pairs, just any set of ordered pairs. The domain of the relation is the set of all the first components. The range of the relation is the set of all the second coordinates of the ordered pairs. A function is a special kind of relation. A function is a relation in which no two different ordered pairs have the same first coordinate. And what we're going to find especially useful in this lesson is this alternative definition of a function. A relation is a function if and only if every value of the first coordinate is paired with exactly one value of the second coordinate. With that said, let's take a look at what we mean by a relation defined by an equation. So the wording you'll see in a book typically will be, consider the relation defined by the equation y equal 3x minus 2. However, that might be written in a little bit more formal way called set builder notation. The way you read this rather odd looking notation here is the set of all ordered pairs of the form xy such that that vertical line that's right in there is sort of a shorthand in mathematics for the phrase such that y equals 3x minus 2. The set of all ordered pairs such that y equals 3x minus 2, or the set of all ordered pairs that make the equation y equals 3x minus 2 true. Now, to get a sense of what that looks like, we can build on an idea that we've seen before when we've talked a little bit about graphing. You might remember when you graph that often what we do is we're looking for some ordered pairs that make the equation true. And what we often do is something like this. We pick a value for x, just anything we want. I'm going to pick several values of x. I want some of them to be negative and some of them to be positive, but none of them too big because I don't want to work too hard. If I plug in these values of x into the equation, I will get the corresponding values of y. For example, if x is negative 2, my y would be 3 times negative 2 minus 2. That's 3 times negative 2 is negative 6, minus 2 is negative 8. If x is negative 1, and some of these I bet in a minute we can do in our head. 3 times negative 1 is negative 3, minus 2 is negative 5. And if we plug in a 0, I bet that's a little bit easier to see. 3 times 0 minus 2, that would give me minus 2. 3 times 1 minus 2, 3 is 1. And 3 times 2 minus 2, 6 minus 2 is 4. Now, we often use these little tables to generate what we think of as a graph, but remember that in that table, all of those entries are really ordered pairs. The ordered pair negative 2, negative 8, negative 1, negative 5, 0, negative 2, 1, 1, 2, 4. So you really can see that that equation is generating a set of ordered pairs, is generating a relation The thing is, these are not the only values of x I could choose. There are millions, in fact, infinitely many more. So this is only a sample of the ordered pairs in this relation. There's many, many, many more. So if there's infinitely many ordered pairs, then the question of is the relation a function and what are the domain and range, that seems like that could be a little bit daunting. But I hope to begin with we see that we get the idea that the relation, that an equation will generate for us a relation. Well, on the theme of graphing, what we certainly could do for the time being is let's just think about these ordered pairs, plot these ordered pairs on a graph, on an XY plane, and see what it looks like. And actually, that's a bad slide there. I did that using a program called Desmos. And this is what the ordered pairs, if you plot the points and draw a line segment between them, you're going to get this graph. And from what we talked about in the previous video, it's very easy to look at the graph and decide is the relation a function and what are the domain and range. As far as whether the relation is a function, you might remember the vertical line test. If you draw vertical lines through the graph, they only hit one point, so that means that the relation is a function. You just declutter a little bit. The domain is the set of all values of the first coordinate, which is represented by the x-axis. And if you look at the graph along the x-axis, notice that it goes forever to the left and forever to the right. So the domain is negative infinity to infinity. The range is the set of all the y coordinates, and on a graph that's in reference to y. And again, this graph goes from all the way as far as you can imagine to the bottom, all the way to the top as far as you can imagine. The range is also negative infinity to infinity. So an equation can generate a set of ordered pairs that is a relation, and we can then talk about whether it's a function and what its domain and range are. One way is just by attempting to draw the graph and taking a look at that. And that connects us in with what we were looking at in the previous video. But it would be really nice, and it's a skill that doesn't come automatically, by the way, it takes a little practice, to see whether we can look at these questions of is the relation a function and what are its domain and range without going through the graph. Let's practice that with this example and kind of let me show you what I mean by that, and then we'll see if we can build on that. So kind of pretend you don't see the graph anymore, you've forgotten what it is, and you want to ask yourself again the question, is the relation defined by y equal 3x minus 2 a function? This is where the alternate definition comes in and where you sort of have to use your imagination. So a relation is a function when each choice of the first coordinate results in exactly one value of the second coordinate. Let's ask ourselves that question. Does each choice of the first coordinate result in exactly one value of the second coordinate? Now here's where you can use your imagination and think about what happened when you chose a value for x. Let's just pick 1 for the time being. In fact, let's literally pick 1. What if we had picked the number 1 for x? And I'm not so much interested in what number I get. I already figured that out. But I just want to ask this question. When I pick that value for x, do I just get one value for y? Or do I get more than one value of y? If I plug in a 1, will I sometimes get one thing and sometimes get a different thing? And I think you can see right away that each choice of the first coordinate really does just give you one choice for the second coordinate. If you can convince yourself that that's true, then you can say, yes, I believe that's a function, even though you haven't drawn the graph. Each choice of the first coordinate, x, results in exactly one value of the second. How about domain and range? Well, let's do that separately. What is the domain of the function, first of all? Now, When we are thinking about the domain, that's the set of all values of the first coordinate. In this case, our first coordinate is represented by x. And a good way to deal with that question is to ask yourself this. What are all the real number values that you can choose for x that would give you real number values for y? Think about every ordered pair that would work. What are all the real number values you could choose for x that would give you real number values for y? And frankly, what's actually a little bit better is to ask the question sort of in the negative sense. Are there any real numbers that you cannot choose for x because you would not get a real number for y? Is there anything you could imagine plugging in for x that would not give you a real number value for y? And if you're wondering how on earth could that happen, here are a few examples of what could go wrong if you choose an invalid value for x. You could take a square root of a negative number. Square roots of negative numbers are not real numbers, and we want to focus on real numbers. You could divide by 0. Division by 0 is undefined. Or, much later in the course, we'll talk about something called a logarithm, and it turns out that you're not allowed to take a logarithm of either 0 or a negative number. For the time being, let's not worry about that one. We'll just put a big weight here on that. But later in the course, when we talk about logarithms, we'll come back to this idea of domain. So what about this equation in particular? What real number values can you plug in for x that would give you real number values for y? Is there any choice of x that would, for example, make you take the square root of a negative number? No, there aren't, because there's no square roots. Is there any value of x that would make you divide by 0? There's no division in there. And logarithms, well, we don't even know what that is yet, but we don't have any of those. What that means is it looks like you can pretty much pick any value of x you want. And if you think back to when we made the table of values and I just started picking x's, I really could have picked anything for x. What that tells me, then, is that the domain is any real number, any number you want from negative infinity to infinity. We'll practice this thought process again, so don't worry. What is the range of the function defined by y equal 3x minus 2? Now, tell you what, finding ranges can be a little trickier, but the question you want to ask yourself is what values of y can you get when you choose x from the domain? Now, again, we're just going to kind of use our imagination. Imagine plugging in some possible values for x and y. We've already done that with some little numbers. But what if we use some numbers that are very large in absolute value, like 100? If x is 100, y would be 3 times 100 minus 2. I think that'd be 298. What if x was something very, very negative, like negative 100? In that case, your y value would be 3 times negative 100 minus 2. That's negative 302. What I want to notice there is that in the first table I looked at, we found some y values that are kind of close to 0. But I think you can see from here that we could end up with y values that are incredibly large in the positive direction or incredibly small in the negative direction. And from that, my intuition tells me that we probably could get any value of y, any real number value of y we can imagine, and the range therefore runs from negative infinity to infinity. Now, if that seems just a little bit too much like voodoo for you, don't worry. We will make that better. We'll feel stronger about this once we look at more examples and particularly the graphs. Let's try a couple more things. Is the relation defined by y equal the principal square root of x plus 3 a function? And what are the domain and ranges? So let's deal with the question of, is it a function, first of all? The question you want to ask yourself for function again is this. Each time you pick a value for x, the first coordinate, do you always just get one value for y? Or is there a way to get more than one? Look at this particular one. You don't even have to write this down, but in your mind's eye, imagine that you first of all, say, plugged in a 1 where the x is. It would give you the principal square root of 4, which is 2. I'm only getting one value for y. Can I imagine any way that if I pick a value of x, I'd get more than one value for y? I don't think that's possible. Each value of x will give you one value of y. I'll just say it real briefly like this. Each x gives one y. That means that what you have is a function. What are the domain and the range? Domain. First of all, domain. In the domain, you're thinking about what real numbers can you plug in for x that would give me real number values for y. And one of the things that I mentioned is that we want to avoid taking the square root of a negative number. Look at this. Excuse me. What if I plugged in a negative 4 where the x is? That would give me the square root of negative 1. That is precisely what I don't want, the square root of a negative number. That tells me that the negative 4 is not in the domain. And so we begin to think about, well, what numbers are allowed? Negative 4 is no good. If I plug in negative 5 for x, I'd still have the square root of a negative number. And by looking at it a bit, you realize, you know what? If I plug in a negative 3, that would give me the square root of 0. That would not be a problem. Square root of 0 is 0. So I can plug in a negative 3. I saw up here that I can plug in a 1. I could plug in a 2 or a 3 or a 4 or anything bigger would give me a positive number under that square root. So it looks like for the domain, the main deal is we can go no smaller than negative 3. We can use negative 3. But then we can use anything we want bigger than that. And that's the domain, negative 3 to infinity. Again, if that seems just a little bit like hocus pocus right now, as we go through this course and get really confident with different kinds of functions, this will become second nature, I promise. The range. Range, again, is kind of tricky. The question for range is when you pick a value of x from the domain, what possible values of y can you get? And the kind of thing you can think about here is that when you take a principal square root, like we have up here, principal square root, that is, by definition, the non-negative square root. That means when you take a principal square root, you will not get a negative number, only 0 or positive numbers. And that kind of tells you that the range would go from 0 to infinity. And if you're feeling like, that's just an awful lot of jumping around, I wonder if I can reproduce that myself, you can always, either with a graphing calculator or by hand, sketch the graph. And if you look at this very plainly, this is a function. This is just the graph of that equation. The domain clearly is negative 3 to infinity, and the range is 0 to infinity. So we can always fall back on a graph if we lose confidence. Couple more. Is the relation defined by x equal y squared a function? So again, the question is, pick any value of x. If I pick a value of x, do I get just one value for y? So let's make a little table in our head and pick some values for x. And when I do this, I think we'll explore a number of facts, actually. If I pick some of my negatives and positive numbers, like this, I think you'll see a little bit of what's going on. Negative 2. Is there a real number that when you square it, you get -2? No, there's not. There's not. Now, that doesn't mean that the relation is not a function. That just means that the -2 is not in the domain. -1 causes me the same problem. 0 is okay. If x is 0, the value of y that would make that work is 0. What about 1? If x is 1, now think about any value of y that would make that true. 1 would certainly work. 1 squared is 1, but also -1 works too. -1 squared is also 1. What that's telling you right there is that a choice of x can lead to 2 values of y. We really don't have to go any farther. That automatically tells you that this is not a function. And as we looked at this table, we get a sense for the domain and the range as well. Notice that we were not allowed to choose negative numbers for x. That tells me the domain is only from 0 to infinity, including the 0. That's okay. And the range, well, let's look at some values there. Notice that I'm getting both positive and negative numbers for y. As I choose larger values, I don't like 2 because it's not going to come out to be a pretty number. What if I pick a nice number like, let's go all the way to 100. There are 2 values that would make that true, 10 or -10. And notice that the range includes large positive numbers, small negative numbers, and basically everything in between. I believe that range is -infinity to infinity. Again, we will later be able to analyze this far better, but for right now, here's the graph, and I think you can see that all of these things are true. That's not a function. The domain is 0 to infinity. The range is -infinity to infinity. Let's try a couple more. The relation defined by y less than or equal to x plus 2, is this a function? So again, dealing with the idea of a function, the question is, each choice of x that you make, do you just get one value of y? Let's pick a value of x. Let's pick anything. Let's pick 1. Y is less than or equal to 1 plus 2. Y is less than or equal to 3, in other words. So y could be 3. But y could be anything less than 3 also. It could be 2. It could be 1. It could be 0. Oh my goodness, I think this is really, really clear here. If you have an inequality defining your relation, you're not going to have a function, because when you choose a value of x, there are actually many values of y that will work. So this is not a function. As far as domain and range, we'll start with the domain. And ask yourself again, are there any values of x that you would not be able to use? Are there any values of x that would, for example, require you to take a square root of a negative number? There's no square root in the equation, in the inequality. Is there any value of x that would make you divide by 0? There's no fractions. So we're going to say, and we'll bear this out with the graph, that the domain is -infinity to infinity. And the range is going to be very, very similar, especially because of the inequality there. We're going to have, for any x, infinitely many choices of y, and as the x's get larger, the legal values of y get larger. I believe this range is also -infinity to infinity. We will talk about graphing inequalities much, much later, but it turns out that an inequality gives you an entire region, and this fails the vertical line test in a huge way. Every time I draw a vertical line, it hits infinitely many points. But you can also see that this region, so that means it's not a function. You can also see, though, I think that the region reaches to negative infinity, from negative infinity to positive infinity in both the x and y direction. So the domain and the range are both negative infinity to infinity for both of them. Another example. And again, we'll grow in confidence as this goes along. How about this one? So, is it a function? I'm going to try to do this with fewer values, writing fewer things if I can. Does each value of x give me only one value of y? Does each value of x give me only one value of y? If I imagine a number and plug it in for x, is there any way that I could get two values for y? No. You pick any value of x, you're just going to get some y, one single y. So the answer to this question, does each value of x give one value of y, is yes, and that means that it is a function. Domain. What values can you legally plug in for x? You can plug in any value of x as long as you are not dividing by 0 or taking the square root of a negative number. This equation wouldn't have you do that. This domain is negative infinity to infinity. Now, range is a little bit trickier. And I would not feel bad if you don't see this right away. You might rely on looking at the graph for a while. But here's what you look at here. Notice that whenever you square anything, you get a positive number. So if my equation says that I'm looking at 5 minus a positive number, I'm always looking at taking something away from 5. That means that the biggest value that y could ever take on would be 5, because otherwise I'm taking away something from it. If x were 0, in fact, my y would be 5. But anything less than 5 is possible as well. If you follow that, and again, this may take some building of confidence, I believe we could say that range is negative infinity to 5. Now, we will soon learn how easy it is to graph an equation of that form. Oh, I lost the picture. Well, it's a parabola that opens downwards. With a vertex, a highest point of 5, it looks pretty much like that. We're going to look at one more, and then we're going to stop because we'll be out of time. Oh my God, look at the different variables in here. So I want to make a point here that the variables in an equation do not have to be x and y. They can be something else. The variable, a little notation here, or definition rather, the variable that's associated with the first coordinate is called the independent variable. The variable that comes first is playing the role that we usually expect x to take. The variable associated with the second coordinate is called the dependent variable. The second coordinate is taking the role we expect y to take. So if that will help you kind of see what to do, that will help a little bit. Is the relation a function? So my t is like x. If I pick a value for t, is there any way that I could get more than one value for s? I don't think so. So this is definitely going to be a function. What's the domain? Remember that one thing I said is you're not allowed to divide by 0. Negative 4, if I plugged it in for t, would make me divide by 0. The way I can represent this is I can say the domain goes from negative infinity to negative 4. Don't use negative 4. Skip over negative 4 and go 4 to infinity. Negative 4 to infinity. That way I'm skipping negative 4. Here's what the graph looks like, by the way. I hope that helps.